recently in getting robots to work in multi-object containers. So to give an example, for example, if you have a robot that is trying to reach into a container like this, where there are multiple objects, and some of them are rigid objects, like boxes here, some of them maybe deformable objects, like teddy bear here. And if the robot wants to get this object with the star on it, then the question that I am interested in is how can the robot plan actions like reaching in there, contacting those objects on that side, predict how they will move, and squeeze, in the case of the formal objects, to move out of the way so that the robot can then reach for the object that it wants to get at. And that's the picking from multi-object containers, physics-based picking example, where the robot needs to reason about the physics of all these objects interacting with each other. And you can also think of the reverse of this, which is the packing operation, but the underlying problem is very similar. If you want to insert an object into a box like this, where you want to achieve some tight packing, the robot may need to reason about reaching in there and nudging those objects to the side to create some space there and insert the object that it wants to put in there. And again, it requires the robot to reason about the interaction of the objects in there. So based on this goal, I have been recently working on this EPSRC fellowship, which is recently running until the end of 2026, and it is titled Robotic Picking and Packing with Physical Reasoning. Now, mainly I am interested in, and I have always been interested in, planning and control. So how can we generate a robot motion to perform tasks like this? So we have been building, for example, planners. Just to give one example of such a planner, this is a robot that searches for objects inside a shelf. So you can give an object that it needs to find, and we have the camera on the hand of the robot. So this is, for example, an example where the robot is actually reasoning about how to push these objects to the side to search for a hidden object. And this is a system which integrates a physics simulation with some reinforcement learning. So it is actually combining two methods together. But then you can kind of see the physics rollouts here at the beginning. And you can ask the system to search for different objects. And here you can see the physics rollouts. And this is also kind of the input that goes to the neural network to basically determine how good certain states are, but also to the gray area here are the hidden spaces where the unseen, the object that we're looking for maybe hiding. But basically, without going into too much detail, this is like just an example application where I'm trying to say that this is the kind of planning problems that we have been interested in building. And like another example is this, where this is the actual scene. This is the simulation model, so the current, representing the current state of the scene of the environment. And so what we are we have in local planners where the path of the robot gets green object, then the robot is deciding to push all of them to the side like that, and it really needs to reason about how all these objects are interacting with each other, obviously, and this just updates from the real scene at any moment of time. And this is a case where, for example, it is even reasoning about how these objects will be interacting with the back of the shelf here. And this is a successful case, but actually, this planner fails more often than it succeeds. So this is a very difficult task. It's a video, but because predicting how all these objects will move accurately is a difficult task. So it definitely doesn't always work. But these are the kind of problems that I have been interested in terms of planning and control. But I will start today my talk actually not with planning and control. I will get to planning and control, but I will first start talking about perception, because in both of these videos that I showed, in this case, there was actually those those AR tags that we have used to detect where all the objects were. And then in this case, we were actually using the motion capture markers to detect where the objects were. So in some of our work, we are actually kind of sidestepping the perception problem by just putting markers on objects and assuming that, okay, assuming we have perfect perception, how can we do the planning and control? But of course, like, something that we realized is actually we do at some point need to be able to use cameras and point cloud sensors and possibly tactile sensors, not just markers on the objects. So we have been looking at that problem of perception in such environments as well, and it's worked with my student Tisam Shu and postdoc Professor Papalas. So we have also been thinking about perceptions. I'll talk about this a little first, and then go into the planning and control bit. So in perception, yes, you have a scene like this, and then existing camera systems that we have for pose estimation, we can use in these kind of systems. So like, you can attach a camera and look at the scene. And then one problem, of course, is that you don't see everything, right, in these kind of cluttered environments. So there's occlusions. And there's particularly even more occlusions. So for example, like you can use to detect objects like this, you can use some pose estimation system, like exist pose estimation systems. So for example, DOP is one, a famous one, which is called deep object pose estimation. So it's a deep learning method that has been trained. So you just give the image to the current image to this neural network, and it tells you where the objects are in this space. Okay? So you can use systems like that. The problem is then, like, as the robot goes and manipulates objects, one issue is that the robot hand starts blocking the objects, potentially the objects block each other, but still you can actually kind of keep running DOP, right? You can run this pose estimation system in this scene and then get where the objects are. And then when you have a scene like this, you can run the pose estimation system in that scene and this scene, and you can now maybe see the target object, and then you can get that. So that will be fine. But the problem is this kind of system, pose estimation systems, work only at a given time frame. So what I mean by that is you give it the image, it gives you the pose of the object. Okay. So what this means is that if at any point the objects become obstructed or invisible, then these systems actually cannot see that object. So just to give an example, so here we are pushing this object, and we want to be able to track it. Okay. So now, by the way, in these examples, I also had trackers, motion capture markers on these objects, but they're only used for ground truth. Okay. So the results that I show, the tracking results I show are not using these markers. These are so that we have the ground truth so that we can see how much error we are making. So now we will try to use this image that you're seeing, camera image, to track the objects. So this is what we want to do. So if we just use DOP, so if you just use vision, this is what DOP does. It tracks the object looking well. Now it loses the object because it's mostly obstructed. It cannot see it. And then once it reatters, it gives some bad estimations, and then it gives something good, but then the hand blocks the object again, and again is lost. Okay. And it is another case where there are no obstructions now. The hand is pushing, DOP is good. Once the hand blocks the object a little more, then it again goes crazy. So okay. One thing that you observed though is that, so I'm interested in physics-based planning and control, and I was thinking, okay, computer vision people who develop these systems, they mostly think of the problem as given an image, you're an output. But actually for robot manipulation, we actually have one more piece of information that computer vision people don't have. We know how our robot is moving. So we have encoding information from our robot. So what it means is that if we have an initial good estimate of where the object is, and if we know where the robot is at the beginning, which you do, and if we know how the robot is moving, which you do, these are available information, then we can also predict how the object is moving based on physics, right? So maybe we can combine, we don't only rely on vision, don't only do vision on the pose estimation, but we can do physics plus vision. So the green one here, what you see is, it is actually both using this camera image, but also it is making, basically running a physics simulation behind the scenes to merge the vision information with the physics predictions to get a more, it is not perfect, but it is much more stable, and it is much more closer to the actual object. So basically bringing the physics predictions together with the vision predictions to make such detection. So what it does is, given this scene, basically we have the robot motion formation coming from both encoders that they go into a physics engine. The vision also goes into the physics engine, and then we estimate an object pose, and then this object pose we just keep iterating over time, so that we just use the previous estimate to run through the physics and then filter them through vision to get a better estimate. This is just Bayesian filtering basically. It's a particular particle filtering scheme that we implement, and you will see that here actually. So here what we are showing now is the particles. The green things that you're seeing are the particles. The blue one is the ground truth. So that is the one that is coming from the motion capture marker, is the blue one. And the green ones are estimates, and the yellow one is again the DOP, the vision only baseline system. And so you can see that we are actually constantly estimating and updating our belief about where the object may be. Okay, so I think in this case DOP is yellow here. Okay. So and what is nice about this is that this is useful not only for tracking one object, because now we can actually track multiple objects, because then you can even make use of the fact that if an object is going and hiding behind another object, you can use the fact that when you're pushing this object must be pushing that other object. So you can update the position of that other object as you are pushing this object that you're seeing, right? And this is now starting to look more like that scenario that I showed at the beginning, right? You have multiple objects in a bin, and you're rummaging through them, and then you want to be able to have an estimate about where all those objects are. And here again, we are running that physics-based, physics plus vision method in there, where you will see that even if we have very high occlusions, we are actually able to come up with quite a stable tracking of all these objects. And if you just do vision-based, just image-based methods, then most of them just fail. For these objects, they will just lose those objects. Okay, so, and this is just showing some, this is basically comparing yellow one here is the vision-based picture, and the green one here is just the error with respect to the ground truth that we are making with respect to the baseline methods. And here again, pushing multiple objects. See how much hidden this object is, but it's normally impossible for this to be tracked with just a vision-based method. Good. So okay, that was the perception bit. And now, yeah, the idea is to then use it in that we're moving towards, and we are still working on the problem, trying to integrate more sensors like that, sensing, technical sensing. But now, as I mentioned, I am mainly interested in planning and control as well. And one problem with the planning and control in such spaces for robots is that it is computationally very expensive and very high dimensional. So if you want to plan robot motion in such spaces, you don't only need to think about the robot degrees of freedom, but also the degrees of freedom of the whole scene, and including the poses of this object. And if you have deformable objects, you can possibly have infinitely many dimensions. But so the issue is that this is a very high dimensional problem. Therefore, it becomes difficult to plan in. And the other thing is that it's not only high dimensional, but it's also computationally very expensive. So if you want to be able to run simulations in such environments, it is costly. So what I mean by this is, with today's simulator, depending on the scene complexity, you can maybe achieve 10 times real-time speed. What I mean is, if you want to simulate a push of 1 second, you can probably do that for a relatively complex scene in 0.1 seconds in a simulator. You can simulate 1 second of real time in 0.1 seconds, but you cannot really go much lower for complex scenes. Okay. The problem is, for many existing planning methods, motion planning methods for robots, we need to query the dynamics model, which in case is the physics simulator, thousands, sometimes millions of times. So when you have when you have only 10 queries to stay real time, it's definitely not sufficient. So that is one of the main problems in physics-based planning and control that we have been dealing with. So we have explored two different approaches to address these two different problems. One is using approximate dynamics. So we have been thinking of, okay, how accurate our physics predictions need to be? Okay, how accurate do they need to be? So, and if we can trade off accuracy of prediction with computational expense, that is something that we explore. And I'll talk a little bit about that. And the second is dimensionality reduction. So given a scene like this, how much detail do we need to have in this model of the world so that we can solve the problem at hand, and whether we can just simplify it so that we can reduce some of the high dimensionality and solve the problem in a simpler manner. So in terms of, like, I'll first talk about the approximate dynamics bit. And the main idea here is, can we actually come up with computationally cheaper physics models? This has been worked together with a PhD student and a postdoc with Magro, and then Daniel Ruprecht is a professor at Technical University of Hamburg. He's a mathematician mainly in robotics, but this work, as I will talk soon about, is basically about numerical integration, but doing coarse numerical integration, and Daniel's an expert in that, so this was a collaboration between our group and his group. But the main question we asked in this is, how accurate does our physics model need to be, right? And if you think about it, your physics model in tasks that you want to perform, the physics model doesn't need to be always at the same accuracy. It depends on the task. Sometimes one example, one daily example, I also show a robotic example, but like one daily example is, imagine yourself reaching in your kitchen, reaching into a kitchen cabinet with wine glasses, very fragile, and you're pushing and moving them around. And then imagine again reaching into a cabinet, but let's say it's all full of plastic containers that are empty, right? So the accuracy with which you will be modeling and the speed with which you will be acting in these spaces are different, right? When you are manipulating the fragile wine glasses, you actually need to slow down, think hard, and then make detailed predictions. So this also applies to robotics. So here is an example where this robot, the task. So this is what I call a high accuracy task. It's a low accuracy task. Basically, it's the same task. It is to push the object, this object, this big thing, into the green circle. So in this case, we need to push it into this green circle. In this case, we need to push it into this green circle. And of course, we don't want the object to fall off the platform its own. So in this case, the object shouldn't fall off the table. In this case, the object shouldn't fall off this strip. And the thing is, so we are running the same controller here. Okay? But what you see is that the controller basically adapts to the needs of the task, because in this case, the physics predictions need to be really high accurate, because if the predictions are inaccurate, the object may fall off the strip. And if the predictions are accurate, it's very difficult to hit the target, right? So actually the system slows down and pays the cost of high accuracy physics predictions, okay? And here, the object does, it's very difficult, even if there's very high uncertainty how the object will be moving. It's fine. We know that the object won't fall off. And it is easy to hit the target. You just aim for the center. Even if you're off, you will still perform the task. So the physics predictions can be really cheap and coarse, and that will be fine. So this is an example of how you don't necessarily always need the same accuracy in your physics predictions. So you can trade off computational expense and accuracy. So we have been thinking about, okay, can we have an abstract physics model? So what is a physics model? A physics model is, our states and controls, state X, control U. So X is our dynamics model, right? And X tells us how the state changes with the time, X dot. That is our most general expression of the physics model. And the idea is whether we can have actually not only one F, normally that is what we have. We have a simulator that just tells us how things are moving. But instead of that, can we have multiple physics models? At the bottom, we'll have 5 models. These are the most accurate models, but computationally expensive. At the top, we will have coarse models. These are very much not accurate, but much cheaper. And then maybe we have the spectrum of models in between, and then we can pick and choose which model we want based on the task. And then one question becomes how to generate such a spectrum of models. And one thing that we have explored is using fine and coarse physics models. So what I mean here is that what I'll talk about, we actually do assume that we have one fine model and one coarse model. And you'll be right to ask, okay, where is this coarse model? But this is, let's say, our favorite physics engine. Let's say Mujoko. We use Mujoko in this work. But you will be right to ask, where is this coming from? And I will talk about that. But in this, we assume that we have one coarse model and one fine model. And then, because if you have that, then actually, together with during our collaboration with Daniel Ruprecht, who I mentioned at the beginning, actually there are numerical integration schemes where you can mix the one coarse and one fine model to get a spectrum. So, and this is achieved through parallelization. But basically, so let's say you have a coarse model. So here the cylinder is pushing this box, and so your coarse model is quite unrealistic. Let's say it moves like this. But as you can see, this box isn't really moving how it's supposed to. But this is we have a very simple model of how the box should be moving as it is being pushed by the cylinder. This is a manually coded coarse model. Okay. So what we need this coarse model to be is we don't need to be very accurate, but we need to be computationally very cheap. Other cheap models you can think of manually is that you can assume, for example, that the object that you're pushing, it is basically glued to the pusher, to the cylinder. So you can, another coarse model you can just update the position of the green box based on the motion of the blue cylinders, and you can just move it forward. And that will be amazingly cheap, right? You don't really need to compute any dynamics, any contact normals, anything. You just move the green box together as the blue one is moving, right? So that's another example of a coarse model. And so this is, in this particular case, we use a manually coded coarse model, but I will show later that we actually then also use learned coarse model. So training a network that and use it as a coarse model and combine it with a physics engine. But I will get to that. So, okay, so this is our coarse model, let's say. And then you have a fine model. The fine model is running the physics in your physics engine. So this is how the box actually moves when you integrate your physics engine at small time steps. So this is very computationally expensive, but this is how this box should actually be moving. Now, the method that we looked at was looking at taking these two predictions and merging them together through what is called parallelized integration to get a task-specific model, like I mentioned, which is not as accurate as the fine model, but it is much cheaper than that. Okay, so and it will, for example, predict that the box will be moving like this, but at much cheaper expense. And the way this parallelized integration, okay, how do we merge the coarse model and the fine model together? We achieve this through parallelization. So just to give a little hint of how this algorithm works. So this is achieved by, so imagine the situation is numerical integration, right? So here on the horizontal axis, this is your time horizon over which you integrate. Okay, so let's say you are trying to take steps into the future to see how your system is evolving over these time steps. And in this method, at the beginning, we start with the coarse integrator, so it's the cheap but inaccurate one. Okay, so let's say here, just as an illustration, your coarse method says that these are the values of your system at each of these different time points. So you run this coarse integrator. The important thing is that this is supposed to be very, very cheap with respect to your actual integrator. Okay, so in the ideal case, this should be negligible with respect to your actual integrator. So let's for a second now assume that this is actually negligible. Okay, this is very cheap. So then what you do is you have estimates for initial points. So let's say you have 4 parallel cores on your machine. So you are able to run 4 parallel simulations. This coarse integrator gives you initial points for 4 slices of your integration. So you start from those points, and then you run the actual computationally expensive physics engine, but starting from those points in parallel. So now what you have done is you have paid 1/4 of the price that you would pay if you were to use the fine model on the full thing, right? So, but then you don't stop here. What you do is you actually, so there is a particular propagation rule in here, but basically you look at the difference between these two and then you update the next step, you update the next step using the course integrator again. So basically in the next iteration of the algorithm, you use these red predictions and you still use the course integrator to make a full sweep again and update your estimation. Okay, so now this is our estimation of how the system evolved. And we ran the course integrator 2 times and the fine integrator 1 time. And assuming these are negligible, we have only paid 1/4 of the price. Now the thing is, basically at this point, so this algorithm works over iterations, but what you do is you basically look at how much change there is at each of these cases, and once the change is small enough for your liking, you say, okay, I convert, I'm stopping. And ideally you stop before the number of iterations is less than your number of course. Otherwise, you didn't gain anything, right? So in this example, if you reach iteration 4, then you already paid the full price. But ideally, you don't do that. You step earlier. But what happens is that when you do this, then this gives you new starting points. So you just keep doing that. Then from those starting points, you run things in parallel again. You get new points. You do the new course integration, and so on. Okay. So this is how we did it. And now going back to just to make the case that it's like, as the course model, you can use a manually hand-coded model, but we also thought, okay, so we have these neural network systems that are being trained, you train it on boxes and cylinders and in your data set, and then you have a new scene where there are triangles. And these systems that are not perfect. They make a prediction about how these objects may be moving, but they're not great. So can we actually use a trained neural network as the course model, but use the simulator itself as a fine model so that we integrate them? So we also played with that idea. So where we would in Mujoko, we will run lots of simulations, but this is the expensive simulator, so that we generate lots of data, and then we will train a neural network. So we will have a course model for Mujoko, that's the trained neural network. And then we would use Mujoko's course model with Mujoko itself as a fine model to do parallel time integration to then be able to make predictions of Mujoko, but that is faster than Mujoko would actually make because we are, when we can, using the course model itself, right? So, and we have applied that to pushing multiple objects at the same time, for example. And we have shown that we can achieve that. This plot is basically showing the mean square of our prediction to the actual one, and this is in log scale. So with the number of iterations, we are able to show that we are actually getting quite small errors. So this has been part of the approximate dynamics approach that we have explored in the past. And as I mentioned, the second thing is, oh no, I have one more thing to talk about here. Sorry, approximate dynamics. But I'm going to change the topic a little here. Now we are particularly going to talk about particular planning methods, which there are these class of methods which are popular in contact-based motion generation for robots. They're trajectory optimization methods, and they are unfortunately very slow in these contact-based environments. So we have also looked at how we can use approximate dynamics, like how can we approximate things within this case as well. And this is where my PhD student David Russell and postdoc Raphael. So in trajectory optimization, you have a very familiar formulation of a trajectory. So you have states X and controls U, and this is your trajectory up until time horizon T. Okay, and without going into much detail, when you do gradient-based trajectory optimization, basically you are computing gradients of the system. For example, you need at a certain time step, right? So this is a certain time step, and you need to compute such matrices at each different time step. But for given time step, you need to compute a matrix like this, which basically looks at okay, how a certain system variable is changing with respect to a certain control. So as you change a certain control a little, what does it say? It says as you change, let's say this is how much torque we apply to a certain joint. So this says, okay, if as the torque I apply to this joint changes a little, how is the object one's X position change, right? So this is kind of saying that. So, but you need to basically compute these big matrices so that you can do gradient-based object optimization. Okay, and you need to compute these. And the way, so when you need to compute these, if you have your dynamics and your cost and everything as analytical functions, you can actually take analytical gradients. So you can just take the derivative of your expressions and then compute these. But when we have these contact-based formulations about multiple objects, that is usually not possible. Okay, so what happens in trajectory-based optimization for robotics is these are computed using a method called finite differencing. Finite differencing, a method to numerically compute the derivatives. So basically what you say is that what you do is that if you want to know how this state variable changes with respect to this control, what you do is you run your simulation one step with a certain control, okay, with a certain value in the control, and then you add epsilon to this control, and then you run your simulator again, and you look at when you change this epsilon, how much this changed, and you divide it, and you numerically approximate it. Okay, so what you did is you ran your simulator at least twice to compute this expression, basically. So you're trying to see how much a certain variable is changing with respect to another a control in your system, and you wiggle those controls and you look at how it changes, and that is how you numerically approximate an EPSRC. And then you do this for all time steps, all the expression. And the thing is, this computing these derivatives is what takes the most amount of time. So this is like using a trajectory optimization method called IL2R, which is a process regulator. And you don't need to understand all of this here, but basically this shows the iteration time on the vertical axis of an IL term. So please only look at the blue ones here, and you can only look at just one of them. So this is just basically how it scales the horizon. But we can just let's look at 50. So what this says is that each iteration of IL2R takes this much time. When we are using for this walker case, when a robot is trying to walk and run, takes this much time. But each iteration takes about 12 milliseconds. And this blue, which is the amount of time it takes to compute the derivatives. And then in IL2R, there's the forward and backwards pass. So VP is backwards pass, or FT is forward pass. So the forward pass and backward pass are taking this much time. So as you can see, actually, the bottleneck is computation of these derivatives, within which we need to constantly run the simulator forward to compute these matrices. So we said, okay, so this is the bottleneck. This is what is taking so much time. And so we have been working on, and the green one are basically where we particularly attempt to reduce this time to compute these derivatives. The thing that we have been focusing on is basically, so this matrix is for a particular time step. But now what I will show is that I will show not only one step, so this is time now, the horizon, okay? So, but in particular, I will show the value of this particular derivative over time, okay? So because we have this matrix computed for at each time step, now I'm showing the value of this over time. So what we have noticed is that actually these derivatives, sometimes they change a lot, this value, over the time, but sometimes they don't. So we have been looking at, for example, not computing these values approximately, but identifying key points and then just approximating them. Again, like you're approximating the dynamics basically about how objects are changing. And you may be asking, okay, how do you get the key points? We have looked at different methods. For example, one of the methods we have been looking at is looking at the jerk of the system. So this is the third time derivative of the system. So we have assumed that when the jerk of the system is high, then these derivatives might also be changing much more rapidly. So basically, you look at the value of the jerk in the system, and when the jerk is high, we sample at much higher frequency, and when the jerk is low, we sample at much lower frequency, and then approximate. Okay, and we had actually recently looked at applying this to many different problems. So pushing the bus, pushing objects in cluttered, lifting a ball like that, and like, this is called a cheetah problem. Now, cheetah is running on a space, and the Walker one that I showed before. And we have shown that we are able to solve all these problems with the approximated dynamics. And we get different speedups depending on the problem. Like in this case, it isn't taking it, like the speedup is not that much, just 1.2 times. But in other cases, we had really significant speedups. And we actually tried this on different simulators as well. So these are from Mujoko, these are from the Drake simulator, which is another simulator. So we tried to show that we can actually apply this to different simulators, different tasks. And we have shown that we can get quite a bit of speed up while still solving the tasks. Okay, so it is 4 to 4. Yeah, okay, I think that's okay. So dimensionality reduction. So, and this is really related. So in this case, we are trying to approximate dynamics, but similarly, we have been asking the question of, okay, instead of solving this high dimensional problem, can we actually solve a simpler problem, right? So maybe I don't want to solve this problem, but I want to try to solve this problem, which may be easier to solve, and then I can see if it works here. And by the way, verifying if a certain robot motion works in a model is much cheaper, because then you just need to do one rollout, right? If you have a possibly working robot motion, verifying if it works or not isn't that expensive. So you can just instantiate this and just roll out it and see if it's working. But planning is when you mostly query the systems many times. So if you can plan in a simplified manner and then just verify in the more complex case, then that might be an advantage. So we have been looking at that. And we have particularly for now applied this idea to deformable objects. So this is with Sheng Wang and Matteo Lenotti is a lecturer at King's College, who we are collaborating with on this. And we have been looking at deformable object manipulation. So if you have a towel like this, and you want to plan to fold the towel like that, for example, if you actually use the original model of the towel, these are very high dimensional, very computationally expensive. So the question has been, can we actually, given the task, can we solve a simpler task? So for example, can we extract a simplified model of the object like this? The important thing is the simplified model depends on the goal, depends on the task, right? So again, an example from life. If you have a t-shirt, okay, how do you model a t-shirt? Depends on what you want to do with it. If you want to fold your t-shirt neatly, you probably need a very good representation of all the details. If all you want to throw your t-shirt into the laundry basket, then you may not need a very high-dimensional representation of your t-shirt. And then again, it depends on that. So what you want to do with it depends on, determines how detailed the model should be. So we have been looking at a method where we have the object, then we have the goal, what we want to do with it. And then from that, we extract some key particles, which we use to do model simplification and also even simplify the action space as well. So we simplify both the dynamics model, but also the actions that the robots can do on it. And then we use an optimization method or planning method on those simplified models, and then reach the final state. And you will be asking, okay, how do you do the model simplification? Basically, how do you determine the key particles? So we have been looking at 1D and 2D cases, like where linear objects and more close-like objects. But basically, with the linear objects, let's say this yellow one is the given goal. So we basically start with only two nodes to represent the object, and we look at how good a match it is. And then if the error is too big, we add more detail to it, more detail to it, more detail to it, until we think that we have a good enough model to capture the detail that is needed at the goal. And we use that for the close-like structures. We do something very similar. So here, this is like the yellow one is again the goal. The goal is just holding a cloth into like that. But the illustration is exaggerated. This axis, the z-axis, exaggerated here, because otherwise you wouldn't be able to see it. We'll just check here on top. So it's not real life, it's just like derivative. Yeah. So then we fit triangular models, trimeshes to that. So here we use two triangles to fit. We check if it's a good fit. If it is not, we increase detail, increase detail, increase detail until we have a good fit to it. So then this becomes our model, and we extract a dynamic model from that. And so what we do is then, like, so if we have a task like that of folding the towel into two, what we do is we extract a certain simplified model. So this is the model for this one, and we run the planner on this. This gives us a candidate plan. We run that candidate plan on the original model. We check how good this is. As you can see, the plan here isn't great. It's trying to do it. It's not great. We use this stage to add more details to the model. We plan again. We test again. We add more details and more details until the detail is sufficient that we are happy with what happens in the original model, so that we avoid planning in the original model, but we have something that is working in the original model. And this is basically showing that we had speed up, right? Planning for original model versus we plan it final. Now, this is just showing that this is like, this is just showing that in action. This clock is correct, right? Okay, so I'll try to finish in a couple of minutes so that we get time for questions. That's good. Okay. It's not fast. I see. Okay. Yes. So the thing is, like, what we have now is open, but we have recently also been interested in tracking these objects as well. So here, like, the very out of the oven thing that, like, my Spirit Schengen has been working with. So we actually want to connect this in an NPC manner to do real tracking. So we have been looking at tracking the deformable objects so that we can then run these planners in a model control manner, constantly updating the actual state. So here what you have seen is Schengen, my students. So this is real data. This is our simulated model. What we're showing is that we are, as we are holding the object, we are able to track the object's position and deformation. And we are interested in doing that so that we can then close the loop on the system. That is, again, we're interested in the perception aspect of things as well. But here, what you're seeing the real point about the changing, reaching in and folding, and what you see here is tracking of it. It's quite good. So we have been looking at closing the loop there. Yeah, so this is mainly what I wanted to talk about today. Very briefly, like, we are also interested in multi-object grasping. So in these kind of environments, sometimes, imagine you're packing an Amazon box or taking things out. Sometimes you want to grasp more than one object, multiple objects. And that's interesting object manipulation problem, grasping multiple objects at the same time. And we have been looking at that problem as well. And we have until now mostly focused on grasping multiple polygonal planner objects. So they are simplified things, but we are interested in generating grasps that look like these, where we can stably grasp multiple objects at the same time and evaluating whether given a grasp we can have them. And this has been a collaboration together with Ken Goldberg at University of California, Berkeley, that we have worked on, and also together with Wisdom, who was my PhD student who then visited Berkeley for this collaboration. But basically, this is so these are grippers that say what you want to do is you want to check, given a grasp candidate, whether this grasp holding grippers will be able to grasp these two objects. If you run the physics simulation on this and check each grasp, it basically takes too long. So what we have been doing here was to put it briefly, coming up with necessary conditions for such grasps to work, so that given grasp candidates, we can filter out the grasps that do not meet the necessary conditions, but we still need to verify them in physics engines, okay? But what happens here is that these objects are already clustered together, but what the system does is, it's given all possible grasps, it chooses the ones that will work, right? Okay, so here there was a mistake, for example, so it doesn't work perfectly, but in general, what it does is it's able to filter out using the set conditions 93% of the inadmissible graphs and only checks using physics the 7% to decrease the physics simulation time. So yeah, but in summary, I talked about perception, tracking objects, and using physics together with video to do that, using approximate dynamics and physics models, speed up the planning, doing model certification on deliverables and multi-object grasping. And I'm happy to take any questions, but before that, I want to do some advertising. So we are hiring at least lecturer in robotics. If you are, or if you know anyone who would be interested, deadline is 19th of March, so soon. You can go to Jobs Leads AC UK, and if you search for robotics lecturer in robotics, you will be able to find the job, for instance. And you're very welcome to contact me as well if you want to ask questions about this. Good, yeah, thank you very much.